I don't know if, oh, we can see it. Okay, I don't know.
Yes,
yeah, that's better. Yeah. Okay, so the next speaker is Hua Bui from Curtin University in Perth, and she's going to talk to us about necessary conditions for non-intersection of collections of sets. So over to you, Hua.
Yeah, thank you, Matt, and thank you everyone for attending my talk. So my talk is about the non-intersection of the collection of sets. It sounds a little bit strange to many of you here, but this is the building block of many known geometry property in variation analysis, like extremality, transversality, stationarity, or subtransversality, etc. So this is the joint work between me and Alex Kruger, so who is in the audience as well. Okay, so let's start with the convex separation theorem. Convex separation. So given two convex set and x bar is a point in the intersections, under some assumption, then we will have a.
We just see your title slide at the moment.
Oh, really?
I don't know if other people also see the same, but I only see the title.
I can see the slide.
Yeah, but okay. Only the first page, right?
Maybe the title slide is the best.
Okay, so so you only can see the title slide.
Yeah, I see slide 1 of 21. Is that the same for other people?
Okay, then I will stop sharing here, and then I'll just share the standard.
Okay, I just saw convex separation for like 1 second, and then.
Before you stopped sharing, there was something.
Maybe it's.
I think I saw something too.
Okay, so can you see something now?
Yeah, it's now in page 2 also.
There it is.
Okay, thank you. Yeah, who we are? Yeah. So there we will have a hyperplane separate two sets in geometric sense that one of the set belong to another one half space, and then another set belong to another half space. So there is another there's a separation in another sense as well, which is a dual sense. So there exists a dual vectors in a dual space, which is non-trivial, different to 0. So that is belong to the normal cone at one point of one set at this point x bar, and also the opposite normal cone of another set at x bar as well. So equivalently, so can you see the slide now?
Yes.
Okay, thank you.
But it's still is slide 2 or 3?
I think that this is the same slide.
Oh, you changed from slide number 2 to slide number 2.
Anyway, so if you can see here the intersection between two normal cone non-trivial, which is different to the sets only contain 0, which means that is contain another vectors rather than 0. So recall that the normal cone of a convex set at the point is the supporting hyperplane of that set at those given point. So for the convex separation theorem for the dual meanings, has many applications like the KKT conditions or subdifferential rule and many more. And of course, we here know that it has a this has played the core role in convex analysis. So how about the for the non-convex case? For this case, we don't have any hyperplane that geometrically separate two sets, but we still have the dual vectors that one of them belong to the normal cone of one set and also belong to the opposite normal cone of another set as well. So there must be another, so the separation here must have a, for the non-convex case, should be formulated in a different way so that that property can capture this assistance of the dual vectors, the separation in dual sense. So for the, so this is the idea of extremality property. So for a pair of sets, this is extremal if for any epsilon, So for any small parameter, there exists a small translation with the magnitude is less than epsilon, so that is make the system has empty intersection. So if you look at here again, the two set, if we move the set A a little bit arbitrarily small along the red line here, you can see that the system here has empty intersection. So this is the idea of extremality. And for the local extremality, this is because we are dealing with empty, non-convex set. It is more make more sense if we only consider the system in a local neighborhood around the given point x bar. So when the dimension of the of x is finite, then the local extremality imply the existence of the dual vectors. So that is belong to, well, the normal cone of one of the set and then the opposite normal cone of another set. This is recover exactly what we want from the convex separation theorem. So look at here. This one is an old setting we considered before. This one is a new setting. So this one is a normal cone of the set A at x bar, and this one is a normal cone of the set B at x bar. And keep in mind that here we are considering the limiting normal cone. If we consider the Fresher normal cone, the normal cone of the set B as x bar here will be empty. Yeah, so this result only hold for limiting normal cone, and that is why we consider just dimension, the finite dimension of the space, finite dimensional space. Well, but not just extremality can be formulated or can be is formulated as in the behavior of the in the empty intersection of the set under a small translations. We also have like stationarity. So stationarity property is a weaker than extremality property, which can guarantee the dual separation as well, the existence of that dual vectors. And we also have the approximate stationarity, which is the weakest property. Actually, it's equivalent to the existence of that dual vectors. And we also have the transversality, subtransversality, semi-transversality can be written, can be formulated as is this setting, the intersection of the collection of sets. For the intrinsic transversality, we formally is defined in a dual space, but in this paper we have we derive an equivalent property in primal space in a Hilbert space, and this property can be rewritten as in the geometry property with the intersection of collection of set as well. And also we have also Hilbert and nonlinear property. All of them can be considered as in the intersection of collection of set. So so there must have a building block for all of these property. So that we can unify this property, and then we derive like one building block, and then we study that property of this building block and derive other and derive all the other property desired for this geometry property. So the building block we come up with is instead of considering the statement that for every epsilon there is a translation. Now we just forget about that. We just given any translation, actually any vectors v, and and epsilon is about it of the magnitude of v. So v belong to the this unit ball, and such that they is make the set A and B from being non-empty intersection become empty intersections. So this one is a building block of all the other property we are considering before. So naturally, we're going to study the matrix characterizations, of characterization, and dual characterizations. But in this talk, we only interested in dual characterizations to see that if we have something similar like the dual vectors that belong to one of the normal cone and the opposites of the normal cone. Well, things not that good, but we have some, we don't have exactly what that property, but we have something similar. Or something quick. So here we consider the X is the so X is the absolute space, and then X is the absolute space, but it's only for when we consider the normal cone is the Fresnel normal cone. But if we consider like Clark normal cone, we can just consider it as a Banach space, and then A, B's are closed set, and then X is a point in the intersection. This is the setting we consider from the beginning. And if we have any vectors V, so that it make the set has empty intersections, then for any parameter lambda1 and lambda2, we will find in the neighborhood of X bar a point A and B and a dual vectors, so that these three conditions hold. So the first conditions make sure that X star is not a trivial, is not zero. The second condition to bound the distance between X star to the normal cone of the set at the point A and B. The third condition is the most interesting conditions because this hasn't appeared in extremal principle. Because if this one is to define the direction of X star. So if we imagine that if we consider some normal cone and the normal cone of the set at A and B here is too big, and which means that the information carry on from this second item here is not really important because the normal cone too big. But these conditions tell us that it does tell us that where exactly the direction we're gonna stick into, we're gonna consider for X star. Yeah, but if N is a Clark normal cone or a convex normal cone, or X is a the norm is differentiable, then we will have the exact inequality here. So we don't need tau, so tau equal 1. So we know exactly what is a vector X star. So so if we consider the so now we try to recover what extremal principle has. If the dimension of the space X is finite, and then we take epsilon go tend to 0, and then because we are in finite dimensions, so the unit ball is compact. So that we will have a, if we convert to a dual vectors X star, so that due to the first item here, we have the magnitude equal, the norm equals 1, and due to the second item, we epsilon converts to 0, which implies that D2 quantitative equals 0, which means that X star belongs to the normal cone of one set, and then the opposite normal cone of another set. Yeah. So what about the empty intersection setting? So this is the gap between extremal principle and convex separation theorem, because even if when two set here is not in, has empty intersection, we still can consider, say, for this case, like A and B, so that they of the shorter distance, and we will still have some kind of normal cone, they opposite each other. So we still have some separation behavior happen there. So how can we capture this this case? So if we consider the building block again, we will see that the these conditions is required. V is actually is small because the norm of V must less than epsilon. That is why the building block here doesn't work for this case. So we have to update the building block so that it can cover the for the empty intersection as well, and give us more freedom. So instead of consider V here, we allow V to be as big as it can, but not bigger than the distance between the set A and then the set B with that translation. And of course, we need the empty intersection as well. So for this building block, we have analogous. We have the same result for dual characterizations with the assistance of the point in the neighborhood. The neighborhood here we choose because lambda 1 and lambda 2 is arbitrarily, and then they assist a dual vectors so that is equal the norm equal 1, and then it satisfies this. It's not too far from the normal cone of the set A and B, and then it's had the stick to this direction. So let's see what we have with the non-empty intersections settings. So we have take A and B are the closest point. And then for any epsilon, we will consider the vector V is here. So that is why it is important that we need to have we allow to have vector V, the translation, big enough. But with the condition that this inequality hold for epsilon. And of course, we have this one as well, because now we consider A, B is empty intersections. So we satisfy the conditions for this building block. And now we have the dual characterizations for this. And then if we take epsilon, in finite dimensional space, if we take epsilon convert to 0 and then tau convert to 1, then we have this property. So this property hold with A and B are the nearest point of two set A and B. So this is just one of the application of the building block we create. We can use this building block with many other purpose. For example, for in Hilbert space, we have something nicer because we can get rid of the tau I mentioned before. The tau. So this is the tau. This is constant tau, which is to make sure that the direction of x star is close to these vectors. So in Hilbert space, we actually can get rid of that, and we can set tau equal 1. So with the same conditions, we have very nice property. So this one is actually our x star. So when we get rid of tau, we know the exact formula for x star. This is the vector x star, and we satisfy this inequality. Okay. So in Hilbert space for the settings A and B here, we do the same arguments. So we will have that if okay. So we will have that when the space is finite dimensional, which is and then we set epsilon convert to 0, then we have this nice result. So this one is x star. This minus x star. So this is in Hilbert space. So just keep in mind that in Hilbert space, we know exactly what is the formulation for x star. So now let's do some other, checking some other settings. So if I make the set B here just equal the, just a singleton, just one vertex, and B here is not in A, so A intersect with B is empty. And we have, so we will have that, so if A and B is close enough to be the, if A is close enough to the projection of B onto A with a tolerant epsilon, then for any neighborhood we choose, this is lambda. So then we have a point in the neighborhood of A, so that this condition hold. So this condition doesn't seem very attractive, but if we reverse the statement a little bit, we will have, if we say that if there is a neighborhood, so that the infimum of this distance of the vectors here to the normal cone of the set A as a gram is bigger than a constant, then we know that the A minus B is bigger than the distance here plus a constant. So which means that this is tell us, quantify us how far it is from A being a projection of B onto A. So this idea is actually very useful in to study the alternating projection method. So it's actually this property is actually named as a distant degree, distant degrees by Dvorsky in 2015, and this is for axis in Hilbert space. Okay. So let me explain again what is the theorem is about. So if we have the set A here, this is a set A, and this is a point B, and this one is a projection of B. So this one is the point A. So the question is how far it from being for A being in a projection of B. So in order to answer that questions, to find this one, we consider the neighborhood of A, and then the intersection of this neighborhood with the intersection of this neighborhood with the set A. So this is the region. And then we also consider on the X that X belong to this neighborhood of B as well. And then we calculate the angle between the neighborhood, between the vectors here, B minus X with the normal cone of A at X here. If this angle is always bigger than a constant, then we know for sure that the A minus B here, the distance between A and B, this one, is bigger than a distance between B to A with plus a constant. So this one so this is the proof, so I'm going to skip the proof. But so this theorem is very handy because basically it studies the building block of the alternating projection. So for example, imagine that this one is the set A, and this one is your A, and this one is your B, and this one is the projection of A on B. So this is quantified to tell us that what is the gap between the distance between Y to A, like so now is a B to A, and then A minus B. So we will have this inequality. So this inequality will derive the basically tell us that for any interaction of the alternating projection, we will have that the distance between like x plus 1 minus x xn minus plus 1 to xn is very big, and that is why this property guarantee the linear convergence of the alternating projection. Well, with that building block, we can derive many others conditions for the convergence of alternating projection as well. So here is some food for thought. So because we are considering the settings where we have a non-empty intersections, that's why we have the linear convergence here. So imagine that here, let's look at this inequality here. So imagine that x minus y is actually bigger than d, a constant. So which means that for every step of the alternating projections, it decreases by a constant, at least a constant, which will guarantee the linear convergence of the alternating projection. So, but here we have the intrinsic transversality is a formulations for a, for the setting would have empty intersection. How about another analogous property for empty intersection for the settings to have the to converge from linear convergence to finite convergence of alternating projections. So the talk is based on mostly on this paper. You will find the metric characterizations on this paper, and then the slope characterizations in this paper as well. And then this one is to study the intrinsic transversality. So thank you very much for your attention.
Thanks very much for your talk, Hua. Open to the audience for questions now. If anybody has a question, you can just. So while people are thinking then, so most of the stuff you talked about was just with two sets,
Yes.
right?
Yeah.
So is the situation analogous for 3 or more sets? Or
yeah, it's analogous for finite set. I'm not sure about infinite.
Sure. But so everything sort of follows through, and you can still derive some kind of result about finite convergence as well for 3 sets?
Well, how? No, so because alternating projection is for 2 sets. For more than 2 sets, we don't know what is the the order of the projection, so I'm not sure. So the alternating projection is only for 2 sets, and the intrinsic transversality is also for 2 sets as well.
Right. So the intrinsic transversality just being for 2 sets, something needs to change there. And for alternating projections to cyclic projections, you need to somehow encode something about the order.
Yeah.
In the notion. Okay, understand. Thanks.
I have a question.
Yes.
Hoa. So very nice talk. You said that there is a result that the distances are in the limit they are 0 when the dimension is finite.
Distance is 0.
Yes, you got the result that the distances are equal to 0. You take a limit.
Yep.
When the dimension is finite, you can do that.
Yes.
Do you have a counterexample for the case of infinite dimensions?
Yeah. So first of all, now at the moment I don't have counterexample for that, but if for infinite dimensions we don't have the compactness, so which means that I think I do have, because for example, consider this space of circles, and then for each x star here, if it is just like 1 0 0, and then so for infinite dimensions, we it's probably easy to find counterexample when the unit ball is not compact. I mean, in the convergence, in the strong convergence.
Okay, thank you, Hoa.
Okay, I think we have time for one more question. If anybody else has a question.
I'll ask a question. Thank you for an interesting talk, Hoa. I don't know if you can even see me. It's sometimes buggy here. Are there any kind of, so just in terms of thinking about the relationship between this extremality and error bounds, are there any kind of interesting objects that you're interested in looking at that maybe are things that are used in math programming? Like I know, and I don't know that much about about this stuff, but I know that in working with Bruno Lourenco, right, he's interested in error bounds for things like cones and conic feasibility, but all the problems that I know of there are convex. So are there any kind of like interesting sort of non-convex sort of objects that people are interested in learning about and that this could be used for?
Yeah, so actually I'm really, this is my question as well. So if you can ask, yeah, this is my question as well. So I think this theory is probably very useful, but I don't really know other, like you said. Yeah, probably this is my future research direction.
We'll find one. There's got to be one out there.
There's got to be one out there.
All right, thanks for a good talk.
Thank you.
Okay, then I think we should move on to the next speaker then. So thanks again, Hua.
Thank you.